Hey, AP Chemistry, how are we doing today? Mr. Oglesby here. So today we are going to be continuing our notes on Unit 6, Thermochemistry. And today's set of notes is going to focus on stoichiometry and calorimetry. Now what that means is you will need to make sure that you've got your calculator today to do those calculations, all right? So let's go ahead and dive on into this. So first off, enthalpy. Well, for enthalpy, we're going to be talking about internal energy. So internal energy is going to be that energy that is inside of that system. So it's the sum of the kinetic and potential energy of all the particles in the system. Okay, so everything that is there. And to solve for our internal energy, we're going to use the change in energy equals Q plus W. Well, what is Q plus W? Q represents heat. Okay, Q would be the heat that we're talking about. W represents work. Okay, so we are hitting a little bit into our physics here with work, and I am going to make sure that you know how to solve for work here in just a little bit. So your delta E stands for the change in the system's internal energy. So how that energy is either increasing or decreasing. Q represents heat, W represents work. So my example here says calculate the change in energy if Q, the energy, the heat, equals negative 50 kilojoules and the work, W, is positive 35 kilojoules. So your change in energy equals Q plus W. So your change in energy equals Q, which was negative 50 kilojoules, plus W, which is 35 kilojoules. So my total change in energy is going to equal negative 15 kilojoules. Okay, so then this would be our answer in terms of just that change in energy. Okay, so very, very simple, very straightforward. Just plug in your numbers and add. Okay, now we've got another question here. So it says for a gas that expands or is compressed, work can be calculated by W, work, equals negative P times the change in volume. So negative P would be your pressure times the change in volume. And our for work, the units that we are going to be using in chemistry is going to be liters atmospheres. So you're going to take your atmospheres and you're going to multiply them by your volume. So pressure times volume. Okay. So my question here says, calculate the work if the volume of gas is increased from 15 milliliters to 2 liters at a constant pressure of 1.5 atmospheres. So we're looking for work. We're working towards that work. So work equals negative pressure times the change in volume here. Okay, so work equals negative 1.5 atmospheres times the change in volume. So your change in volume would be your final volume minus your initial volume. So your final volume is 2.0 liters minus your initial volume, which was 15 milliliters. Now we do need to make sure our units are the same. So we've got liters here, we've got milliliters on the other. So I'm going to go ahead and convert that. So 0.015 liters. Okay, so I just converted that into liters. Okay, essentially moved that decimal 3 times. Okay, so now it's just a matter of plugging in my numbers into the calculator. So we're actually going to get rid of this because all that was supposed to be was the work. So work equals negative 3.0 atmospheres. So you're going to get 1.5 times 2, essentially. And so negative 1.5 times 2, that would give us 3. And then that would be what you do to solve for work. All right? And so this would be our final answer. All right, so that would be it for just kind of the general looking at our work and looking at our change in energy. So moving on, let's look at actual enthalpy. Now remember that enthalpy is basically just going to be that change, that total change in energy in the system. Okay, so it's that change in that internal energy. So enthalpy, there's a couple different ways that we can actually solve for it. So we can use stoichiometry, calorimetry. We can use something called Hess's law. There's also something called heats of formation, and then there's the bond energy. So there's 5 different ways to solve for enthalpy. Today, we're going to be focusing on these first 2. So stoichiometry and calorimetry. Okay, so for stoichiometry, essentially all we're doing is we're going to be taking and we're going to be looking at this and see, okay, here I've got a change in heat. Well, if you look at this right here, that's essentially a conversion factor. That's a mole ratio that we can use. We know that for every 1 mole, I have negative 368 kilojoules. And so I can use that as a conversion to solve for energy given a certain mass or volume or whatever. Just use my stoichiometry to solve for it. Okay, so let's do it. So it says, using the reaction above, calculate the heat change that occurs when 3.5 grams of sodium reacts with excess water. Okay, so remember, anytime they say you've got excess of something, that means that it's not going to be a factor. It means that I've got so much of that substance, I'm not going to need to even bother with it because it's not what is going to run out. Okay, so that tells us that our sodium's probably going to be the thing that runs out. So I have 3.5 grams of sodium. And we always start our stoichiometry with the number we're given, with what we know. So I have 3.5 grams of sodium. It's not what I'm looking for, so I drop it low here. So grams of sodium. We do that because we're canceling out that unit. And we're going to go to moles. Why do we want to go to moles? Well, because we know of a conversion of moles into energy, and that's in our original problem up there. So I'm going to go from grams of sodium into moles of sodium. How do I do that? I do that using my molar mass. So for every 1 mole, I have 22.99 grams. Okay. Now, again, I look at this and I see moles of sodium is not what I'm looking for, so I drop it low. So moles of sodium, we cancel that out, and we're trying to solve for heat. So we're solving for that energy. So we do know of a conversion to go from moles into kilojoules. We can do that using this number right here. So I have, for every 1 mole, there's negative 368 kilojoules. Okay, well, is kilojoules or heat or energy what I'm looking for? Yes, it is. So I can go ahead and solve. So 3.5 times 1 times negative 368 divided by 22.99 divided by 1, we're going to get negative 56 kilojoules is the heat change that occurred as a part of that reaction. Okay? That's all it is. Essentially, all we've done is we found another conversion factor to use in our stoichiometry, and we just use that as a way to get from moles into energy. Okay? Now, this next part is a little bit out of place, but there's not really any other place to put it. So here it is. So essentially, all I need to talk about is what's the difference between an intensive and extensive property. Just kind of remind y'all of that. Remember, an extensive property is going to be anything that depends on the amount that you have. So when we talk about extensive properties, what we're going to be looking at is, okay, stuff like length or volume or mass. Those things all require us to have certain amounts of a substance we're talking about. For instance, if I've got like this grapefruit, if I cut it in half, what changed? Well, the size changed, right? The mass changed. All those kind of things changed because I've got a different amount of this substance here. Okay? Intensive properties, on the other hand, do not depend on the amount. So again, this grapefruit here, it is essentially like an orangish red color. So it's orangish red, and if I cut it in half, does the color of the skin change here? No, it doesn't, right? That would be an intensive property. It doesn't depend on how much I have. Now, 2 things to recognize. The heat of the reaction is an extensive property. So the heat that reaction is going to actually produce or absorb is going to be dependent on how much you have of that substance. Temperature, on the other hand, is an intensive property. So how much you have does not change what the temperature would end up being for that substance. Okay? So just kind of something to keep in mind when you're looking at these things. Heat is extensive versus temperature, which is intensive. So a common misconception is temperature and heat are the same things. They are not. Okay? All right. So moving forward, so now let's talk about calorimetry, because we've already talked about stoichiometry, right? So calorimetry is going to be the measure, or that science of measuring the flow of energy. So we're measuring how that energy moved, either gained or lost in a reaction. And it is going to be based on the observation of temperature change being absorbed or released by something. And what we use for calorimetry is a calorimeter. Okay, why would we use that? Why would we call it that? Well, we're looking at, essentially, we would be using that for stuff like calories. And so that's where that's falling into. That's the category that we use for that. So then we've got heat capacity. It's also called specific heat. So the heat capacity is basically us looking at a substance and seeing, oh, well, this substance is going to take this much energy to change its temperature by 1 degree if it's got 1 gram of that substance. And so the specific heat capacity is basically us looking at a substance and saying, okay, well, how much energy does it take to raise this substance by 1 degree Celsius? Now, here is something that I think y'all probably should know, is that the specific heat capacity for water is 4.184 joules per gram degree Celsius. Now, I'll say most of the time AP is going to give you this, or they're going to have it on a table of yours. Probably they will be giving this to you in the problem itself if you end up needing it. But this one is a very commonly used specific heat, so it sometimes just makes it easier if you just know it. Okay, so water's specific heat capacity, again, liquid water, okay, so not solid water or not gaseous water, just liquid water, its specific heat is 4.184. Okay, now, constant pressure calorimetry is a type of calorimetry. Essentially, in that case, what we're going to see is that the pressure is going to remain constant throughout the entire process. It is simple, and it is used to determine the heat of the reaction. Essentially, the reaction is going to occur in a solution. The temperature is going to increase or decrease. And then whatever we've got, the insulating cup that it's sitting in is going to prevent that heat from being lost. Now, in your chemistry class, you probably did what was called a coffee cup calorimetry. And we take 2 coffee cups, we nestle them inside one another, and then you have a thermometer that sits down in there, and you're measuring that change in temperature as a part of the reaction. Okay? Now, energy released as heat is going to equal the heat capacity times the mass of the solution times the change in temperature. And so we would call that Q equals MC delta T. I call it Q equals MCAT. Now that is why we've got a cat right there, because Q equals MC delta T. This looks like a cat right there. So Q is MCAT. So that heat is MCAT. Mass times the specific heat times the change in temperature. Now, something to remember with calorimetry is the amount of heat lost equals the amount of heat gained. And so when we're looking at that, you can essentially take this formula here and you could say, okay, well, heat gained equals heat lost. So positive MCAT equals negative MCAT. And that would allow us to actually solve for any of those variables as long as we've got the other ones. Okay? So, for example 1 here, it says a coffee cup calorimeter contains 150 grams of H2O. That's a mass at 24.6 degrees Celsius. That's a temperature. And then we've got a 110 gram block of molybdenum, which is a mass, and it is heated to 100 degrees Celsius. That's a temperature. And then that's placed into the water in the calorimeter. The contents of the calorimeter came to a temperature of 28 degrees Celsius. So this is my final temperature right there. Okay. So then they want to know, what is the heat capacity per gram of molybdenum? So I've got 2 masses. I've got 2 temperatures. I know the specific heat of water. And then I've also got my final temperature there. So what I'm going to be using here is MCAT equals MCAT. So heat lost equals heat gained. Okay, so now it's just a matter of plugging in our numbers here. So I've got my molybdenum, which was heated to 100 degrees Celsius, and I've got my water, which was at 24.6. So what's going to be losing energy and what's going to be gaining energy? Well, remember, energy goes from high to low. So we're going to move from the hot temperature to the cooler temperature. So that means that my molybdenum here is going to be losing energy and my water is going to be gaining it. So I have negative 110 degrees Celsius times the specific heat of molybdenum, which we're looking for, times its change in temperature. So the final temperature was 28 degrees. Sorry, this is not 110 degrees Celsius. It's 110 grams. Sorry about that. Minus the initial temperature, which was 100 degrees Celsius, equals my water. So 150 was the mass times the specific heat of water, 4.184 degrees Celsius, joules per gram degree Celsius. I'm struggling here a little bit, I guess. And then I do my final temperature, which was 28 degrees Celsius, minus the initial temperature, which was 24.6. And then I'm going to take that and I'm going to plug it all in. So I'm going to solve for my left and right sides individually first. So on my right side here, on my left side here, I've got 7,920 times the specific heat equals 2,115.48. Okay, divide both sides by the 7,920. And we'll find the specific heat for molybdenum is going to equal 0.267, which converts into, when we use our sig figs, 0.27 joules per gram degrees Celsius. And that would be my answer. Okay, so pretty simple. You just plug in your numbers and then you're just using your algebraic reasoning to solve for that. Okay? All right, so moving on, let's take a look at this next problem. Now, this next problem is actually going to be solved a little bit differently in just that you have to make some conversions towards the end that you might not be aware of. So, 4-gram sample of ammonium nitrate is added to 100 milliliters of water in a polystyrene cup. The water in the cup is initially at a temperature of 22.5 degrees Celsius and decreases to a temperature of 19.3 degrees Celsius. Determine the heat of solution of ammonium nitrate in kilojoules per mole. Assume that the heat absorbed or released by the calorimeter is negligible. Okay, so essentially that last little sentence there is basically just telling us don't worry about any of the loss to the environment that we wouldn't be able to take note of. Okay, so how do I solve this? Well, when I'm looking at this, one thing that I need to recognize is there is only one mass, right? And all they tell us is that there is one temperature that is the initial temperature and one temperature that is the final temperature. And so from that, I immediately know that this is going to be Q equals MC delta T. I'm going to use that formula for my equation for solving this. So how do I actually do this though? Well, I'm solving for Q, right? I'm solving for the heat of the solution, but specifically in kilojoules per mole, okay? So how do I do that? Well, Q equals my mass. Now, this is the mass of the solution. They want us to know the the heat of the solution of ammonium nitrate, not just the heat of the ammonium nitrate. So from that, you immediately need to recognize that this is going to use the mass of both the water and of the ammonium nitrate. Okay, so my ammonium nitrate has a mass of 4. And for my water, well, they tell me that I have 100 milliliters of water. Well, remember, for water, every 1 milliliter equals 1 gram. So this is essentially 100 grams of water as well. So I have a total of 104 grams. Okay. Times. Well, now I need to figure out, this is for the solution. This is the specific heat of the solution. Well, in comparison to the 100 grams of water, there's 4 grams of ammonium nitrate. That's very, very, very little amount of ammonium nitrate. And so because of that, the specific heat of the ammonium nitrate is going to have very small effects on the overall specific heat. So what that tells me is that I'm going to use the specific heat of my water instead. So water has a specific heat of 4.184 joules per gram degree Celsius. And then I do my change in temperature. So my final temperature, 19.3, minus the initial temperature, 22.5, both in degrees Celsius. And then I solve. So I'm going to plug that into my calculator, and what I'll find is that my Q equals negative 1,392. And this is 1,392 joules. But my question asks me for kilojoules per mole. So kilojoules per mole. So first thing I should do is convert my joules into kilojoules. So I'm going to do this. I'm going to convert from joules into kilojoules. For every 1 kilojoule, there is 1,000 joules. Solve for that, and I'm going to get negative 1.39. 2. Well, with sig figs, it should just be 1.39. So I should actually go back in and change this to a 0 here. Okay, so 1.39 kilojoules. But they want to know kilojoules per mole. So now I need to figure out how many moles of the ammonium nitrate I have. So I have 4.0 grams of ammonium nitrate. I'm going to convert from grams of ammonium nitrate into moles of ammonium nitrate. And for every 1 mole, I find the molar mass, which is 80.06. I solve that, and what I'm going to find is that I have 0.0500 moles. And so when I'm doing my kilojoules per mole, I would take that, negative 1.39 divided by 0.0500, and I'm going to find that I have a total of 27.8 kilojoules per mole. And that would be my answer. Okay. All right, very last thing on our notes for today is a heating curve. Now, for a heating curve, this should be something that y'all have seen in the past. It's called I call it a heating curve not curve, because a heating curve does not have curves anywhere on it. And so one thing I will make note of is, if you've forgotten how to solve for energy over multiple phase changes, please make sure to go back and review your notes from Unit 3. You can find those on Canvas, but they will kind of talk you through how to go through a heating curve and solve for that. So things to recognize on a heating curve, right here they tell us that this is going to be the change from liquid to gas, which tells me all of this right here is a liquid, and it is 100% liquid there. Whereas during this phase change, what I'm going to see is that it's going to start off mostly liquid and end mostly gas. Okay? Well, if that's the liquid phase, then this would be my phase change of going from solid to liquid, or from liquid to solid, and then this would be 100% solid. Okay, so do keep that in mind. They also tell us that we've got different amounts of energy here. So one question would be to ask, why does it take more energy to go from right here, from liquid to gas, than from solid to liquid? Well, in that case, you just kind of have to think about, okay, well, one's probably going to have a higher specific heat, right? Because it's going to take more energy in the liquid phase, which means it's going to have a higher specific heat. It's going to have that, going to take more energy for it to increase the temperature of 1 gram by 1 degree. Okay. So let's take a look at this problem. It says, how much energy is required to raise the temperature of 12 grams of ice from negative 12 degrees Celsius to 50 degrees Celsius? Now, we are talking about ice. We do have a phase change that's occurring because we know that ice melts at 0 degrees Celsius, and we know it boils at 100 degrees Celsius. So we do have one phase change that occurs. We go from a solid to a liquid. So let's keep that in mind. So I've got Q equals MC delta T. And I'm going to use this for any time I've got 100% of a state of matter. So 100% solid or 100% liquid. So in the case of water, water is going to stay ice. It's going to stay solid from negative 12 degrees Celsius to 0 degrees Celsius. And at 0 degrees Celsius, that's where we're going to start to see it melt. Okay, so that's what we're going to use for our change in temperature there. I'm solving for my energy. I know I have 12 grams times the specific heat of ice. Now, ice is going to be the solid version of water, which is right there. So we know that the specific heat is 2.10 joules per gram degree Celsius. And then we have our change in temperature. So the final temperature in the solid phase is 0 degrees Celsius minus the initial temperature, so minus negative 12 degrees Celsius. All right, we plug that into our calculator and we will find that we have 302 joules. Okay. Now, the next one I'm going to do is I'm actually going to be solving for my energy during the actual phase change, so changing from a solid to a liquid. Now for this, we can just use stoichiometry. So I have Q, and they found that I have 12 grams of it. And we're trying to go from grams into energy. So grams get dropped low. We're going to go from grams into moles first. Now, why am I doing this? Well, I'm doing this because I'm using my heat of fusion, which is again up here in this table. So the heat of fusion is going to be for our solid to liquid or from liquid to solid. And they tell us the heat of fusion is 6.01 kilojoules per mole. And so that tells me of a way to convert from moles of substance into kilojoules of a substance. So I'm going to use that to convert. First off, I'm going to have to find the molar mass of water, which is 18.02. Again, we're talking about water. And then we're going to convert from moles of H2O into kilojoules of H2O using that conversion. So I have, kilojoules per mole. So I have 6.01 kilojoules per 1 mole. Okay? I'm going to plug that into my calculator, and I will find I have 4.00 kilojoules. All right, but I'm still not there, right? I still haven't reached that 50 degrees Celsius. I started off, and I went from solid state, and I got it all the way up to where we started our phase change. So that was what we did here in step 1. Then, after that, I converted using my heat of fusion. I converted from grams into kilojoules, and that's basically how much energy would be required for that phase change to occur. So to go from solid to liquid. So from 100% solid to 100% liquid. And that would be step 2. And then the last step would be to solve for that conversion of 0 degrees Celsius all the way up to that 50 degrees Celsius. So we're going to go back to using Q equals MC delta T. But this time we're in our liquid phase. So Q equals the mass, 12.0 grams, times the specific heat. Now this time we're liquid phase, so our specific heat of water in the liquid phase is 4.184 joules per gram degree Celsius. And then I'm going to do the change in temperature. So my final temperature is 50.0 minus the initial 0. And then I can just plug that into my calculator. So Q equals 2,510.4 joules. Okay. Now, the very last thing they ask is how much energy is required. So really what I need to do is I need to take and add up all the energies that I have. So I had 302 joules plus 4 kilojoules plus 2,500 joules. Now looking at this, we do need to make sure that our units are the same. I'm going to convert that kilojoules because it's only one conversion. So I'll take that, I'll move that decimal 3 times, and I'll get 4,000 joules. So then I take 302 plus 4,000 plus 2,500, and we will find that Q equals 6,802 joules. And that would be my final answer. All right, y'all, that is it for our second day of notes on thermochemistry. Let us know if you've got any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.